ultrasound and photoacoustic imaging of breast cancer. So in 2022, 2.3 million people were diagnosed with breast cancer, making it the most prevalent disease worldwide. And early detection is key to survival. In high-income countries such as the United States, your survival rate for 5 years after diagnosis is an average of 90%. When we look at middle and low-income countries, however, the survival for 5 years after diagnosis drops all the way to 60% and goes lower from there. To increase survival rates, especially in middle and low-income countries, we need a portable and affordable imaging system that could detect breast cancer and then monitor the progress of treatment. So the rationale behind combining these two specific imaging modalities, ultrasound is already accepted as a diagnostic tool. It's safe, affordable, and it can be portable as well. Certain types of photoacoustic imaging are also used for breast cancer imaging, but this specific one swaps out the laser for the LED, and that makes it a portable and affordable device. So photoacoustic imaging sends the light into the tissue, and the molecules absorb light at different frequencies and emit the sound waves. Those sound waves get picked up on the ultrasound transducer. It forms an image and it gives a lot more information than simply ultrasound alone. So my role in the project was making the phantom that was used, or that will be used and is used to test these imaging modalities. So making phantoms, it needs to have a similar acoustic properties as human tissue. It should have vasculature and then a visible lesion. So we started with a lesion. These are several molds that were used. Perfect sphere would be like a benign lesion, whereas more of a normal shape could indicate malignancy or potential malignancy. So there were lots of options when creating that, and you can even change that in the final phantom as well. So then the phantom mold, here's a 3D printed model of a breast that was used to make this clay mold over here. The clay mold has these tubes. Those represent blood vessels. They're just kind of holding the space for when the agar is poured. And then the lesion in the background, they are made of an agarose base, and different concentrations of silica are added to create contrast. You can actually change those, the concentrations of silica based on what you want the imaging modality to detect. So it creates more options as well to really test the modalities. So we pour the base layer, that's solidified. The lesion is placed in the most likely quadrant, where people most likely get breast cancer, and then the remaining agarose is poured and solidified. So then to actually image it, here's our setup. This is the phantom here. This is just a weight to hold it in place. These tubes connect water to a pump back there that circulates water through, simulating blood. This was just the first trial of this. And here's an ultrasound transducer. So using the photoacoustic acoustic X imaging system, these are the results we got. This is only B mode ultrasound. The photoacoustic, the photoacoustic imaging with LED, there wasn't quite enough time to add that in yet. But we have a benign lesion here and blood vessels. The blood vessels are not going to be able to be seen completely through the image because it is a 3D model, but that's expected. Our goal was just to get a good image of the lesion and then also blood vessels. So in conclusion, the lesion and plastic tubing or blood vessels were visible during B mode ultrasound. Both appeared dark as intended. So the agarose phantom was an accurate imaging representation and can be used for future imaging tests. So in the future, now that the phantom making process has been standardized and tested, instead of the clay, a reverse 3D model will be made for the agarose mold. That'll just make it more standardized, because the clay can move a little bit. And then in the future, you can also add oxygenated and deoxygenated blood and add photoacoustic imaging with LED to test the molecular differences. And I'd like to thank Dr. Kothapalli and his lab group, the Penn State Cancer Institute, and CSATS. And here are my citations.